we might be live. No guarantee. As always, somebody has to confirm our existence. Collapse the wave function. Someone said hi to me. I don't know whether that's real. Oh, there you go. People are saying hello. So it must be happening. And check it out. Look at all the people we've got here. Look, it is the crew. Can one of you speak for a second? You're all nicely muted. Man, you're all so well behaved. This is the 5 minutes before we start the show when it just gets...
Yeah, but you have me on the show now.
I know. I thought you would be
behaved.
both a good and bad example for the rest of the new cast members of the Weekly Space Hangout, which is going to be very exciting. They will learn all of your good habits and all of your bad habits. So I'm going to say hi to a bunch of people. Hello to Astro B, Bill Sugden, Bob Harkins, BTT, Christian Woodland, David Dunn, David Fairweather, Giselle Sabrin, Gordon Dewis, Janelle Duncan, Jessica Feltz, Johnny Zed, Kim Barron, Larry Beckham, Martin Bradshaw, Nancy Graziano, Paranor, Powell Zersky, R.N. Stroh, Raj Luthra, Raza Siddiqui, Ryan Schmitz, Susan Hunter, Tim Bargan, Tom Van Scotter, Wayne Francis, Yuval Litvin, and Zapvan. Hey, everybody. Welcome to a absolutely standard regular episode. Who will say happy podcast day? I guess it'll be me. I feel, we don't have Kimberly here.
Happy podcast day.
There we go. Someone has to at some point. The fans now demand it. So, someone says they've got visual but no audio, but other people have audio. Yeah, try. I guess if you don't have any audio, then you won't understand me saying to reset your screen. Yeah, BTT says the cat ear headset is awesome. Beth, how does that thing work? It's speakers, right? And
yeah, so this part is a speaker, so I can actually turn these on externally, but obviously earphones, and then it lights up in different colors if I want it to. Unfortunately, I think the battery's died, so I may have to switch and you won't get to see it anymore.
Well, it's still, I can hear, but you're using a different microphone, but it works as headphones still without the...
No, it has I'm using the microphone on it.
Oh, okay. Where's the microphone?
Somewhere in here.
Oh, okay, all right. Okay.
I just trust it.
All right, well, we're sort of at the 5-minute mark, so why don't we start? I'll put you all back in your boxes here. There we go. There's me. If I'm a little nervous, I apologize. The broadcast is like showing me in my sort of dashboard. There's just this swirling circle for where the live video should be, and at any point it's going to snap and actually function and could cause some noise. So anyway, I'll just have to get on with it. All right, here we go. Hello and welcome to the Weekly Space Hangout for Wednesday, October 9th, 2019. I'm Fraser Kane, publisher of Universe Today. This week we're going to be talking about Saturn has the most moons, Jupiter, the Interstellar comet, mass inflow, outflow rates of the Milky Way, i.e. is the Milky Way getting more or less massive, and an idea for a 2-stage, fully reusable spaceplane. Joining me this week on my screen is Beth Johnson. Beth, hold on, wait a second. You waved, but I don't have you on the screen now. There you go, there's Beth.
Hi.
Beth is, of course, from the SETI Institute. Any aliens yet?
Sadly, no.
Okay, well, let's hope for next time. We've also got, let's see, next on my screen, we got Michael, Michael Roderick. Michael, welcome back.
Hello.
Third.
Thank you for having me back.
This is like your third episode now.
It is,
You're a grizzled veteran at this point. And we've got Sandy Springman back. Sandy, welcome back. Oh, still muted.
Thank you.
You haven't been on this season, have you? Nope. No. You were with us a couple of times last season, but it's great to see you again. I think so. Maybe. but you've got exciting news, so that's why we've got you. That's why we've got you back this week, which is awesome. All right, so before we get into this week's special guest, I just want to remind everybody that that we couldn't do this without our good friends of the Weekly Space Hangout crew. They are, of course, the fans, the executive producers. They're the ones that really make this show possible. Even now, more than ever, thanks to the coordination efforts of Nancy Graziano and the rest of the team to bring in all of the new co-hosts and sort of mix it up and give people a lot more practice in doing their science outreach. And I can't imagine how complicated this is. I don't think Nancy knew what she was getting into when we started to propose this idea, but she's really pulling it off. So, but if you want to be a member of this amazing community, go to wshcrew.space. They will hook you up. They will give you access to the forums and all the behind-the-scenes information, give you your executive producer title, and then you can go and help organize guests and cast members of the Weekly Space Hangout. All right, let's get on with this week's guest. All right, so we've got Marina Kounkel. Marina, welcome to the Weekly Space Hangout.
Hello, happy to be here.
So where are you located?
I am currently a postdoc at Western Washington University.
Western Washington University. You said that's just right outside Vancouver.
Mm-hmm.
Right.
Yeah, we're just right on the border with Canada.
Right. Oh, you're like right north, like almost my Vancouver, not Vancouver, Washington. Okay, all right. I was about to go down that rabbit hole, but no, that's great. I think I've been there. It's right next to Blaine, right?
Yep.
And you've got a wonderful, there's like an observatory and there's a planetarium there. And I actually got a chance to get a behind the scenes sort of with Brad Snowder.
Mm-hmm.
Yeah, who
Yes.
runs the planetarium there. It's so cool and it's great. So what do you do?
So I am interested in star formation and how stars form, and particularly, as you can probably see behind me, a picture of Orion. So I've been studying its structure in detail, and many people think of Orion just as the Orion Nebula, but it's really a huge structure spanning the entire constellation from head to toe, and contains thousands of stars, just as many in the rest of it as there are in the Orion Nebula. Frequently, it's said that young stars, when they form in clusters. And then these clusters, most of them would rapidly disperse by the age of around 10 million years. And only just a small handful will survive later on to the ages of 100 million years, for example. But Orion, well, it's pretty big, and some of it is starting to get pretty old. It's with the ages of around 8 or so million years. And the velocity dispersion inside of it is not really all that big. It's just on the order of a few kilometers per second. So such a region would likely to persist as a co-moving group for a considerable length of time. When we are looking at the sky, well, we do know about some co-moving groups within approximately 100 parsecs or so.
Now, sorry, when you say a co-moving group, that is like a group of stars that all form together from the same solar nebula, and they're still kind of hanging around. I mean, we can see examples like, say, the Hyades cluster or the Pleiades cluster, these sort of more mature versions, while Orion is like something that's, it's still brand new and newly forming.
Something like that. Not necessarily just even as clusters. Co-moving group, well, there is a lot of overlap between all the various terms. So people say OBO associations when referring to these very young extended populations. People say co-moving groups when they think about clusters or other groups of stars that are kind of still have similar speeds, but not very centrally organized. And Pleiades and Hyades are more example of proper clusters.
Right. And you've had a chance to do a lot of work with Gaia, which, I think people who watch the show know that I'm a gigantic fan of the Gaia spacecraft. Nothing has already delivered, like one small mission has already delivered such a range of scientific outcomes, from discovering white dwarfs and neutron stars and the positions of all of these stars in the Milky Way, as well as being able to scan the largest small Magellanic Clouds, and just like build this understanding of how the Milky Way is changing over time. So what did you use Gaia data for?
So I was searching for co-moving groups of stars that are moving similarly, presumably have formed at the same time. And through using some machine learning on Gaia catalog, I have been able to cluster together approximately 300,000 stars within 1,000 parsecs in approximately 2,000 different co-moving groups.
Okay, so hold on. So a kiloparsec, how, like, that's astronomer talk. What is, for those of us who think in light years, how much is a kiloparsec?
It's approximately 3,000 light years.
3,000, right. So a parsec is 3 light years, a kiloparsec is 3,000. So we're kind of imagining this box centered with the sun at the center, about 3,000 light years across, with 300,000 stars in it. And so just for comparison, is the Orion Nebula in that box?
Yes.
Yeah,
yes.
Okay.
Orion is located approximately 1,200 light years away.
And then you discovered co-moving groups within this region. And how many did you say?
Approximately 2,000 of them.
2,000. So is that's essentially 2,000 Orion nebulas at some point?
Potentially, yes. So, I mean, they span all sorts of different ages. Some of them are just shy of the age of the sun. So many of them are very, very, very young. Interestingly enough, approximately half of those stars are part in these long filamentary string-like structures that are approximately 600 light years across. They're all moving with a very similar speeds. There's just a slight variance across the entire length. But these groups of stars, these long strings of stars, they have all formed together, and it's possible to estimate their ages just from isochrone fitting.
So, I mean, we look up in the sky, and those who do like astrophotography, there are some nebulae that you can see. There's, of course, the Orion Nebula, and there are other ones, like I mentioned, Pleiades and others. Some are, and more visible in the southern hemisphere. But with that many groups, does that sort of change your idea of how long these things last for, as like a nebula that would be visible in the sky, and then they start to tear themselves apart?
Absolutely. Well, nebula was really the earliest stage of star formation, when you still have a lot of gas. Gas eventually does go away, but the resulting stars that have formed from the same molecular cloud will stay together, will still move in the same direction for quite a while longer. One of my favorite string of stars is near the cluster Alpha Per. And the structure spans approximately 150 degrees. It's half the sky, really. And it's approximately 60 million years old. And most of these strings tend to go away after a few 100 million years, but it's much, much longer than what we originally assumed.
So then, if we think about the stars that we see in the sky, how much of them are formed together and are sort of starting to dissipate, and how many of them are just like part of the Milky Way and happen to be in our corner of the galaxy this time around?
Well, most of the stars that we see most of the stars that are out there are pretty old. Within this box that I have analyzed, there are approximately 20 million stars, and 300,000 sounds a lot, but it's still just a small fraction.
Yeah, how many stars are there just to give a sense, like how many stars are within that kiloparsec?
On a few dozen million.
A few thousand million, a few billion.
Are these?
Few dozen million.
Yeah.
20, 30 million.
Right. So about, say, a couple of % of the entire Milky Way are in that region. Mm-hmm. So it is a lot of stars. So it actually is sort of needle in the haystack to find these groups that are younger and are still kind of connected together. So obviously then the goal is, can we find the sibling stars that formed with our sun? What are the chances? I know there's been a few candidates, but it's been more like found thanks to the same kind of chemistry as the sun. You know, could we get to some point where actually we can map out that original solar nebula that we came from?
It'd be pretty difficult. The sun is kind of on the older side. Even most of the clustered stars that I have identified, they rarely push past 2 billion years. And even then, at that age, you might just get just a small handful of stars. But by those ages, most of them tend to already completely dissipate into the field.
Yeah, it's funny. I just saw a paper maybe 3 days ago that someone identified, I think, 550 candidate stars that have similar movements. So, but they haven't necessarily checked the composition yet, because I mean, I know there was one that really seems like a twin of the sun. Gaia just feels like this wonderland of data. What are some of the other ideas that you've been thinking about that you could sort of mine out of that spacecraft?
Well, the main thing, particularly with the catalog that we have created, are the stellar ages. And it's easy enough to compare the stellar properties that we see in the populations that are still just forming to the much, much more evolved field of just all the stars that we see in the sky. And whenever we find any sort of discrepancies, well, we don't know where the discrepancy is coming from. Will it dynamically kind of all equilibrate later on, or is it something that is intrinsic? But once we actually do have ages, perhaps we can trace how things evolve directly. So in particularly with Gaia, particularly with the next data release, we'll have much more information on the stellar multiplicity, so all the binary stars, and that will be something that I will be very, very excited to look into.
And we're still only halfway through Gaia's mission. I mean, we've had a couple of data releases so far, but there's still many more to come. So is there some additional data that you are looking forward to?
Well, yes, absolutely. As I mentioned, first multiplicity, and then they're going to have many more radial velocities. Right now, what they have is a lot, but it's not quite enough to actually get radial velocities for all the stars that they're going to get. And their precision is also going to improve, and also hopefully we'll get a better astrometry on the low mass stars as well.
It really is a phenomenal mission. It still kind of blows my mind how precise these measurements Gaia is able to make over all of the astrometric data that's been done before this. I mean, the Europeans with the Hipparcos and other astrometry that they've done in the past, but Gaia is just taking this to another level. Do you think that with this, even this several percent sample of the entire Milky Way, do you feel like that gives you a big enough picture of what's going on across the overall Milky Way?
Well, it's at least gives us a representative version of it. Of course, the further we go, the more complete our understanding is, but even within just a few kiloparsecs, we can learn a lot about the structure and the dynamical evolution of the Milky Way. For example, with these strings, they appear to be preferentially oriented perpendicular to the spiral arms. So that tells us something about, well, because all these strings should have formed from the same molecular clouds. That tells us how molecular clouds are actually forming in the galaxy. And then we can see that the overall shape that is traced by the combination of many strings at different ages does appear to evolve slightly. So, for example, 100 million years ago, there was some event where the spiral arm might have been at an angle of approximately 60 degrees to what we have currently. So that tells us how the structure of the galaxy is evolving.
Absolutely fascinating. Well, I can't wait for the next data release and obviously more research on this. Marina, how can people find out more about what you're working on?
I'm not very active on social media, but by email, marina.kounkel@wwu.edu.
Yeah, that's probably best. I can definitely respect not wanting to be anywhere near social media and instead focusing on doing astronomy work. Well, thank you so much for taking the time to chat with us today. Really appreciate it. And again, good luck with all of your work. I can't wait to see what happens next. Thank you. All right, now it's time to move on to the rest of the show where we bring you up to date on the news.
Microsoft discovered a comet that turns out to look like it came not just from our solar system, not just from our Oort cloud, but from beyond our solar system. It is an interstellar comet, and it seems to be the second interstellar object that's been detected. So the race has been on to figure out what this thing is made out of, and does it look anything like comets in our solar system, or does it look like something completely different? So a group that I'm a part of, including Teddy Carreta, who's another grad student in my group, soon to be a PhD candidate, he got time on the Night Bach telescope, confirmed that there's cyanide in this comet spectrum.
Oh my God, it's 1910 all over again.
Right? Cyanide makes comets look green. So cyanide's great, but it's not going to kill you if the Earth passes through the tail of a comet. So that's cool. It's the first, and then they also identified C2, diatomic carbon, and it's the first time that anyone has identified C2 in any interstellar object since October 1st. And some math, and some more math, and a little more math finds out that this comet, compared to other comets, when you're looking at its carbon chain molecules, is kind of typical. And so most comets in our solar system that look like Borisov are Jupiter family comets, that is, comets that are mostly affected by the gravity of Jupiter. So that seems like Borisov formed in conditions that would pretty much be similar to how the Jupiter family comets in our solar system formed. So does that mean that what we know about our solar system and how things formed here is applicable to whatever solar system that Borisov formed in? And of course, if you look for more molecules like C3 or other sort of variabilities in carbon chain chemistry on this object, might tell us more. But it's sort of interesting that this object came from way out there, but looks really similar to things closer to home.
So if it looks kind of similar to things that are closer to home, are we sure that it came from way out there?
Oh yeah, because its orbit is very clearly hyperbolic. It's got an eccentricity greater than 1. So if you've got an eccentricity of 0, you're a circle. If you have an eccentricity between 0 and 1, you're an ellipse. If you ever made an ellipse with 2 tacks, a string, and a pencil. And then this thing, if you remember your conic sections from high school, pre-calculus or trigonometry, this thing is not a line, it is not a circle, it is not an ellipse, it is not a parabola, it is a hyperbola. It has where it's going from and coming from, it will not come back.
Right. But I mean, even like some kind of complicated 3-body interaction with Planet 9, which is actually a primordial black hole, that kind of thing.
You saw that paper with the black hole, the primordial black hole to scale.
There was a great conversation from Mike Brown when that paper had come out, and he was saying, if it was like it seems a little more reasonable if maybe it's like a hamburger, the mass of a planet, maybe that would work. But anyway, it was that. I resisted the clickbait as best I could for us to not cover that story, even though it really was just like catnip to me and the team. But I saw
that. I get emails from the archive every day, and it's like, oh.
Yeah. So
someone will have fun with that, and it won't be me.
Yeah, exactly. But okay, so I mean, this idea, so let's assume that it is from some other solar system. And I've even heard that they maybe have they think they know which solar system, and they're starting to, there's another paper that came out that made some proposals. I forget the name. Maybe someone in the chat will say the name, and you'll be like, oh yeah, I know that place. You don't. I mean, there's 300 billion stars in a, whatever. But so then this idea, if it does have the exact same kind of chemistry, like was this a surprise?
So some people thought it was going to be a little bit redder, which means that the grains are going to be a little bit larger than, say, your average solar system comet. But our spectra don't necessarily show that it seems to be as red as some other folks have said. So I think it's a lot of this is going to come out in the wash as people just keep pointing bigger and bigger telescopes on it.
Beth, last time we saw an interstellar object, Oumuamua, the world's SETI researchers quickly turned their telescopes on the object to try and see if there's any signals.
As best they could. Yeah.
As best they could. Have there been any plans to see if there's anything going on with this one?
I haven't heard anything specifically, but I'm sure that we have turned the ATA to it, which is the Allen Telescope Array in Northern California. We have a tendency to observe anything that looks interesting, and since it's our telescope, we can do that. So I haven't heard any results, but I'm sure that we're looking at it.
Sandy, I know that we got a little bit a faster jump on this object. We're catching it inbound and not outbound, as what happened with Oumuamua. So do you see more observations happening as it gets closer?
Yeah, I think everyone's going to be pointing everything they've got at it. I mean, if you could observe it, people are going to be observing it. People are going to be applying for telescope time. We tried to get time in the Large Binocular Telescope here at Tucson, and they kind of were like, we thought about it, but try again later. So
when it gets
at some
closer.
point, we'll be hopefully pointing LBT at it. So I think pretty much anyone who's can get telescope time on bigger and bigger pieces of glass to look at this thing and figure out what the spectra does, and does its behavior change as it comes in closer to the sun. It's going to be there's going to be a lot of stuff on the archive, and a lot of people are going to be discussing it.
I mean, how many of these? Like, now we've seen 2. Were there lots of others that we just missed before today? I mean, to see 2 within 2 years seems a little weird. I know there was like maybe another interstellar comet a couple of years ago as well, and I know there's some objects that are orbiting Jupiter in funny directions that could be interstellar in origin and captured by Jupiter. I mean, how often is this happening?
I think some people have done some math on it, and I think also we're now at an era where detectors are far better, they're more efficient, you have all these surveys, it's getting easier to look at more and more of the sky with more frequency. And this object was discovered by an individual, so it is still possible that people and not sort of more automated procedures can be discovering these objects. So I think,
until LSST comes online.
Until LSST comes online. And, when you say until LSST comes online, it's almost like saying, well, when JWST launches.
Which it will. Yeah, no problem. JWST is going to launch. Haven't you seen? They've made it together.
They're all going to launch, and they're all going to come online. I mean, LSST is like, broken ground and stuff, and it's getting closer and closer to being operational. But
and JWST has been put together. It's one telescope now.
Yeah.
So we'll, I think it's going to be interesting as we see more and more of these things, and can, maybe point to where they've come from, and, from other stars, how do their composition resemble the things we see in our solar system, or do they seem a little weirder? Can we get shapes? Can we get, can you start doing population studies? I mean, it was 50 years between the discovery of the first asteroid and the second one, I think. It was a long time.
Yeah.
So
that sounds right.
Yeah.
Yeah. The fact that this is happening a little faster is, it's interesting.
So there's been this talk of like having a solar twin, like another star out there that looks just like the sun, same composition, everything. If the comets form from like the leftover materials of the solar nebula, and this comet looks like all of our other comets, is there any thinking that maybe this came from another star that looks just like the sun, or is this just happens to
be interesting? But it seems like a lot of the other solar systems that we look at look nothing like our solar system. They all, they tend to have hot Jupiters closer in. So does that say something about the initial composition of the disk and how the planets formed? And so is our solar system sort of an outlier and should not be counted? Is that meme too old? So it could mean a lot of things, but I think it'll be interesting to see if our solar system is sort of typical or atypical in terms of the composition of these small bodies, because the small bodies are sort of help what helped structure our solar system the way we see it today, because we're all pretty sure that the giant planets changed where they were in the solar system if they didn't change their positions due to interacting with a sea of small bodies of sort of the leftover protoplanetary disk.
And I know that astronomers have seen clouds of comets around other stars. They haven't necessarily seen, smaller objects, but they can actually see the exo-Kuiper belts. So
right. So this is a good way to start sampling other solar systems with these fun little interstellar objects that come rolling through.
Well, this is the strongest argument for me.
Sorry?
I was going to say this is the strongest argument for me on why the Fermi paradox is so weird, and that one day we and, aliens should be able to send spacecraft to other stars because rocks and chunks of ice can do it. So just imagine if somebody actually wanted to do this on purpose, as opposed, I'm pretty sure we can match the capabilities of a rock. That's my hope. I mean, I'm not sure.
They did it in Starship Troopers, right? That's how they flung those asteroids out to Earth and killed everyone.
Well, there you go. We take all our science from Starship Troopers.
And if 2 Interstellar Borisov is if it is an alien probe, I will eat my shoe, and I will do that on the Weekly Space Hangout. You have my word.
But I will be excited because I will have lots of money.
That's exactly right. Yeah, the city. Yeah, the Allen Array will just be the beginning of a gigantic telescope in the use of SETI. All radio telescopes will be SETI telescopes. Sandy, have you guys got a way that you would scan a spacecraft? Would you fire your radar? How would this work?
Sorry, one more time.
How would you probe with your radar a spacecraft it was coming by? Has this ever been discussed?
I think you could probably see the differences in dielectric constant of the surface. If the thing was really shiny and didn't look like any other asteroid you'd radar it would probably be pretty obvious. And people have been pinging satellites with radar from Earth for some time, so we sort of know what those signals look like. And if you see, repeating signals coming from it, then that's Beth's job at SETI, right? Is this thing emitting any signals that look unnatural?
Yeah. So we know. Well, good. And again, congratulations. I know you sort of downplayed it, but you've been involved in a bunch of papers recently, right? About in
I just
providing
have
your part.
Author.
I
did a thing.
You're on the paper.
I was there as damage control.
Congratulations. Just take a compliment, Sandy. You did it. Keep publishing.
Appendix F out of G for my thesis.
I forget what do you guys call this? Like the number of citations. The number of citations that you've got just keeps going up, and the number. There's some number that scientists use to figure out how far away you are from.
But if anyone wants to volunteer to copy edit this once it gets closer towards being accepted, let me know, and I'll put you in touch with Teddy.
Oh, sure. I'll jump in. I help.
Great.
I'm a terrible copy editor.
I'll send you a cat in exchange.
Wait, no. All right, let's move on. Beth, what do you got?
So Monday, it was announced by Carnegie Science that they have discovered 20 new moons on Saturn, new to us. And that now means that Saturn has 82 and Jupiter has 79. So Jupiter is now losing. All of these moons are about 5 kilometers, 3 miles in diameter. 17 of them are retrograde and 3 are prograde. So 17 of them are rotating in the opposite direction of Saturn, which is really cool to me. 2, they figured out fit in a group called the Inuit group. So it's at an angle of about 46 degrees to Saturn. And they theorized that was probably once a larger moon, and they've just found more pieces of it. All of the retrograde moons, all 17 of them, are actually in another group, and they look like they're in the Norse group. So they're all named for Norse gods. And that was broken apart also from a larger moon. And so, again, they've just discovered more fragments. The interesting one is that there's the final prograde moon was found at an inclination of 36 degrees. It fits in with a group called the Gallic group, but it's farther out from Saturn than that group is. So there's 2 predominant thoughts. One is that it formed with that group and is just somehow moving farther away. Two is that it might have a different origin and it might not be from the same type of moon that was probably broken up. So a lot of these are moons that might have formed early on in Saturn's formation and just got smashed up by things during their early heavy bombardment. And so now they've got all these different fragments and they just keep finding them as we get better and better telescopes.
So is this like because Saturn has rings made of ice that it's more likely to have these small moons? Because Jupiter, with its more mass, you would think would still in the end win. If you could go out and really take a census of every single moon, I wonder in the end who will win. Because these,
I think it's more due to their size, that they have a tendency to attract things that pass by, and then when they were forming, that they kept things near them. I'm honestly still a little shaky on the theory of why Saturn has the beautiful rings that it does compared to, say, Jupiter or Uranus or Neptune, who have rings, but they're not that spectacular.
well, and you're not the only one. I mean, astronomers themselves are going back and forth, having arguments about whether the rings are new, whether the rings are old. So can we talk a bit about just the technique that they use to actually discover these? How are they finding, now there is no spacecraft. We don't have Cassini there working hard at Saturn. What method do they have to actually be able to find these moons from Earth?
They were actually discovered just using the Subaru telescope at Mauna Kea. So they're just getting, since they can do better imaging now with adaptive optics and that kind of thing, it's just easier to take more images and see if things move. So, I mean, that's really at least that's what I've read, is that it's just using a regular large telescope and taking better pictures.
Tim Bargan says, what's the cutoff between an object being a moon or just a large clump within a ring? I mean, these are pretty far outside of the ring. I showed people the picture. And when you look at the picture, like you can see Saturn, you can see its rings right in the very center. I don't know if you're looking at the picture as well. And then you can see the different orbits. Let me just...
Yeah, there's a really good image in the article that one.
Yeah. And so you've got like these prograde and retrograde moons, and then this blue group, and then right down in the middle there's Saturn and its ring. So these are really far away. They look like they're at an inclination that's off from the ring plane.
Yeah, they all are.
Yeah, so this is like a completely different creature than chunks in the rings.
Right. So that's why they think these were orbiting bodies that somehow got destroyed. So either ran into by an outside force like a comet or an asteroid during that early heavy bombardment period in our solar system. Because the reason the reason they think that, the fragments are still there, and if those had formed while before all of the gas and dust had gone away, then that gas and dust would have caused friction that would have caused those planets, those moons, to drop into Saturn's orbit and actually get destroyed by Saturn. So since those fragments are still all out there, they must have formed after the moons all formed, and then they got smashed up later on. So I think like I said, I think it has more to do with the size of Jupiter and Saturn, that they keep attracting all of these large bodies that got broken up later on.
Right. And the other part that I find really fascinating, it was fascinating when there was a bunch of new moons that were discovered around Jupiter as well. Just this idea that you can even have groups of retrograde moons. And that in fact, like you see groups, like it's weird to see a prograde moon when it should be a retrograde moon. That there are moons that go one way around Saturn and Jupiter, and then moons that are going the opposite way, while most of the solar system is all turning in the same direction. Because you got these things that are going backwards, what is the possible, cause? How do you get something to go into the wrong direction orbitally?
Well, it's a very good question. And we see things like that also with Venus and with Uranus being on its side. So obviously some mechanics have happened that we're still trying to determine. I think a lot of it is probably going to turn out to be impact related. Larger bodies hitting things and hitting them hard enough to actually spin them the opposite direction. Because it all comes down to momentum. I mean, you have to switch it somehow. So it's got to be a bigger object, and that would fling it around. There's also the possibility, again, like our interstellar visitors coming in, having these hyperbolic orbits, if something got close enough to get pulled in by a planet, it might already have been going in a different direction. So
Right.
it could come in at the opposite angle and then just be stuck there. So that's also a possibility.
Awesome. Good. I bet this is not over yet. I wouldn't be surprised if Jupiter takes the prize again in a couple of years, and then it goes back to. I mean, they're neck and neck, so it's just gonna,
Yeah, they just keep going. They keep going back and forth.
Yeah.
And the fun thing with this one, like when they discovered the last set of Jupiter ones, Carnegie is also offering to let the public nominate names for some of these moons as well. So you can actually join in the fun and submit IAU approved type names for these moons. So no Moony McMoonface,
No
which I've already
McMoony
seen
McMoonface.
like 12 times.
Of course.
But yeah, you can participate. So I always love that aspect of it. We've done these things a few times at SETI, and so I love when other science groups are doing it too.
That's awesome. Michael, what have you got for us?
So there was a recent study looking at these things called high velocity clouds, which are massive clumps of gas that float around above the plane of our galaxy. And some astronomers looked at how fast they're moving. Are they moving in? Are they moving outside, like away from the galaxy or towards the galaxy? And it looks like the majority of them are moving in towards the galaxy, which means that the Milky Way galaxy is actually gaining mass. So the Milky Way galaxy is getting more massive over time as gas is falling into our galaxy. So
Now this isn't entirely surprising, right? That gravity tends to pull material in, and obviously, over time, the Milky Way has merged and with tiny dwarf galaxies and torn them apart and nommed them up and added them to its mass. So, I mean, you can't be surprised that the Milky Way is gaining mass, but what are the functions that make the Milky Way lose mass?
So this is something called stellar feedback, and it has to do with how stars will actually push out material, push out gas out of not just like a star cluster, like we were talking in the beginning, how these clusters last about 10 million years, they blow out all their gas. They can do that outside the galaxy as well. So you can have a cluster of stars that starts forming stars. The really massive stars are going to die first. They undergo something called a supernova, which is a very explosive event. They essentially blow out the gas of the cluster, and so that gas then becomes unbound. It's not gravitationally bound to the cluster. If it's a strong enough explosion in the right place, it can actually be puffed out of the galaxy, of the galactic plane. And so you get something that they call a fountain model, where you're blowing out gas from these supernova explosions, and then gravity takes over and it starts to fall back in. So it's this feedback process of stars form, explode, blow out the gas, and then that gas comes back. And then that new gas can also form new stars, and it's kind of a cyclical process.
Right. But so that gas, as it's getting blown out, it doesn't have the escape velocity to leave the galaxy entirely. The stellar outflows just aren't fast enough to let them get away.
Right, yeah, it's going to fall back onto the galaxy.
But then there is, in addition, these new, you were saying, like this new flows of gas that are coming into the galaxy. So where's this stuff coming from?
So the authors, they think that this is a confirmation of the fountain model. So this is stuff that was in our galaxy, which got blown out, and then it's coming back in. So this is kind of all self-contained. So you were right that we do have mergers, like we're cannibalizing small satellite galaxies like Sagittarius. I think there's another one I can't remember off the top of my head, but there's multiple small galaxies that we create all the time, and those were just kind of gravitationally drawn in. But what they're looking at specifically is believed to just be galactic material that got puffed out and then just falls back in onto the galaxy. And this is also, these things are not very long-lived. So after about 400 million years, which for astronomy is very short, these will fall back into the galaxy and we won't see these clouds anymore. So this is not necessarily an indication of the entire past history of accretion of the Milky Way. This is more of an instantaneous measurement, that this is what's going on right now. And after 400 million years, we won't see this anymore.
And so, I mean, is it just about how much material is out there? Is it about how much star formation is going on in the Milky Way? I mean, what are the factors that go into defining this?
Yeah, a lot of it's going to be star formation because that is believed to be what's puffing all this stuff out. At the same time, I think I have the number here. The amount that is flowing in, there's a net inflow, so there's a half solar mass inflow versus a 0.16 solar mass outflow. So we've got, it doesn't sound like a whole lot. It's like 0.5 solar masses,
Yeah,
but
half a
that's,
sun.
but that's like every year, and that,
Yeah.
Goes on for millions and
Billions of
millions of years,
years.
and that can supply more gas, more stars to the galaxy.
It's interesting, right? You think about the raw materials that a galaxy has to work with when it first forms, and all of the gas, the pockets that are there, and it's all left over, this primordial stuff that's left over from the Big Bang, and that's all a galaxy has is its raw materials. And of course, if it collides with another dwarf galaxy, but space is big and there's lots of stuff out there, and so you can imagine this stuff making its way into the galaxy over time and adding more and more to the mass of the galaxy and allowing more star formation, encouraging more star formation.
Yeah, that's how we think that a lot of in the past, a very high redshift far, millions, billions of years ago, we had a lot of mergers, a lot of galaxies that were colliding, feeding gas into the centers of galaxies, producing bursts of star formation, and that could very well be what formed a lot of the stars in our galaxy.
That's awesome. All right, so today I was privileged to watch a presentation from a company called Exodus Space Technologies, and I'm going to share some pictures here just so my co-hosts can see this. And so what they're working on is kind of the holy grail of space flight. So just to kind of give you like a little bit of a history here, right from the beginning, as people were working on rockets, they knew that it was incredibly wasteful to launch your rocket, have the whole thing break apart into stages, all the pieces break into the ocean, burn up in the atmosphere, and all you get left is, the astronauts return home in a little capsule and the whole thing goes into the museum. And so people have been working on reusable rockets for decades. And the first idea for the space shuttle was actually this really crazy double space shuttle. So it would have been this big, it looked like the fuel tank, but it had wings. And then a littler space shuttle, the orbiter part, was bolted onto the top of this thing. And then the whole thing, the whole stack would launch. It would disconnect, and both parts would return to the Earth. The orbiter would go up to space and perform its mission, and the fuel tank would fly back down, land at the landing pad, at the runway, and then the orbiter would do its mission, and then it would land, and then the two would be refueled, stacked up, and then away the thing would go again. And of course, that didn't work. The technology just wasn't ready, and so they had to go with the big, large external fuel tank. They had to go with the booster, the solid rocket boosters, and then they were, the thing would launch, and the orbiter, the solid rocket boosters would come off, and then they would land in the water, and they had to be totally refurbished. And then the main fuel tank, the big orange thing, would be destroyed in the atmosphere, and then the orbiter would make it to space, and then it would land, and then that would require a tremendous amount of refurbishment. And so now in the modern age, right, the goal has been thought to build a single stage to orbit. So something like the X-33 or the Skylon, one of these things that takes off, flies to space, does its mission, returns to Earth, gets refueled, and takes off again. And the problem is, thanks to the tyranny of the rocket equation, you actually can't carry even if you have a perfect system, you can't carry much to space. And so, of course, what SpaceX is doing with the Starship is they have sort of cracked the code. They are building a two-stage reusable rocket. So the whole thing launches, the bottom stage comes off, the super heavy booster lands back at the launch pad, and then the Starship portion flies off into space, does its mission, returns, lands beside the booster, they stack back up again, and away you go. So But this idea of a space plane, that you get a chance to use the atmosphere as a lift, as a way to lift, aerodynamically. You get to use a jet engine while you're flying through the atmosphere is still very compelling, as opposed to going to full rockets right from moment one. And so this company Exodus, they've been sort of in stealth mode for the last decade or so, and they've been starting to make some announcements in the last little while. And so their spacecraft is called the Astro Clipper, and I'm going to show people here sort of what it looks like, and I'll show my co-hosts so they have any idea what it is that I'm talking about here. So the plan is, and I'll find a good example of it here. So it looks like a aircraft, takes off from a runway, has jet engines on the back, flies to an altitude of about 18,000 meters, 60,000 feet, and then then fires. So, and it does this as a lifting engine, like as an airplane, flies to this altitude, all on jet engines. And then it kicks on its rocket engines and flies to an altitude of about 100 kilometers. And then it detaches into two stages. So you've got the booster portion, and then you've got the upper stage portion. The upper stage portion fires its rockets, flies to orbit, does its mission, carries passengers, whatever. The booster portion glides back to the landing pad, and both do their missions, land, are refueled, and take off again. And if this works, and this is of course a gigantic if, then we could be at this point where it's like the best of all possible worlds, where you've got a fully reusable launch system that takes advantage of the aerodynamic lift while you're in the atmosphere, uses jet engines when that makes sense. And the other thing that's kind of interesting is that they're going to use jet fuel, kerosene, all the way. So the rocket engines will use the same jet fuel that the jet engines use, and they'll just provide an oxidizer when they get above the Earth's atmosphere. So it's a really fascinating concept. I was really quite impressed to see all of these pieces come together, and a lot of it is like thanks to the sort of the modern age of like the miniaturization of all of the different kinds of technologies. When you think about the amount of computing power that's on the space shuttle or the Saturn V or things like that, they're all shrunk down. The efficiency of jet engines these days is actually, and of hypersonic engines, is a lot better than it was back like even in the Concorde's time. And so you've got all of these technologies all coming together all at the same time, and we might finally get a fully reusable two-stage spaceplane, which I love. They're hoping to launch their first version in maybe 2024, which will be something that'll do some suborbital flights. And then hopefully by the early 2030s, they're hoping to go into full reusable space plane mode. One interesting idea is to like chase down orbital debris, which I like, because, each piece of debris has its own special trajectory. And so to be able to chase this stuff down and actually grab it is a pretty cool idea. So I just, we're working on a video for this, but I was sort of so excited about it that I wanted to talk about it today. So,
still no space elevator though, right?
No, but the funny thing is that space elevators now are, when you look at the incredible unobtainium technology that's going to take, and it's only going to bring you down in launch costs by a few orders of magnitude, it might very well be that you don't need a space elevator anymore, that these reusable multi-stage rockets are going to be able to bring the cost down to the point that you don't actually need to go with a space elevator anymore, is the hope. So we'll see. All right, well, here we are now at the end of our show. I want to give everyone a chance to let us know what they're working on, where people can find out more. Michael, you're still on my screen. Where can people find out more, and what are you working on?
So I am now applying to jobs, which is a lot of fun. I've got my first application next week, so I am pretty much applying to jobs, writing proposals.
Yeah. The fun part of being of getting your astronomy degree.
Yeah, trying to go for a postdoc. I did just create a Twitter account. I am at Michael Roderick.
Nice.
I don't have anything posted yet, but I'll try to get that going. Stepping into the 21st century here.
That's awesome. Well, we will post your Twitter handle in the show notes. Beth, what are you working on? Where can people find out more?
I am posting lots of great stuff on SETI Institute. And as far as my master's degree, I'm working on volcaniclastic sediment dispersal at axial seamount in the Pacific Ocean.
Wow.
My hope is to sort of apply some of this knowledge to solar system moons, particularly in the realm of cryovolcanoes later, I hope, someday. And I can be found on Twitter as Planetary Pan, and I can be found pretty much everywhere as that.
Yeah. And also possibly the SETI Institute Twitter feed. It's possible you have some influence on that as well.
Maybe, just a little.
Sandy, what are you working on? Where can people find out more?
I'm also trying to graduate, and I should be applying to jobs. I'm on Twitter as Sandy, Sondy.
Now, when you graduate, then we get to call you Dr. Sandy?
Yes.
Right on. I cannot wait. Let us know when that happens.
You will be on the list, Fraser, and you and Chris Lewicki can convene the meeting of Team No PhD to kick me out.
Oh, it'll just be me again. No PhD. Cool. And of course, you're Sandy on all the things. So, even on TikTok, Snapchat. Oh, you're muted, or maybe not.
TikTok. I'm not cool enough for Snapchat. Or
Yeah,
TikTok.
that's what all the new kids are using anyway.
I mean, I know people who are older than me who use Snapchat, and I tried. And I was like,
I have a Snapchat. I don't know if I changed it from my old nickname to Planetary Pan though, and I don't really do much with it.
maybe. I mean, TikTok looks amusing, I guess, but I don't really do video.
Yeah. We just got to grab the screen name. The point is, you've got that nice short screen name on everything. You gotta get
Except
it on
some
everything.
some punk has it on Instagram.
No. Oh. And once again, of course, you can follow me at Universe Today. All the things. Put everyone here. Put everybody there. So thank you everyone for joining us, watching this episode of the Weekly Space Hangout. Thanks to my co-hosts and our special guest for bringing us the space news. Thanks everyone watching, moderators. Again, huge thank you to Nancy for herding all of the cats. Hey, have you offered to give her cats, Sandy? She's really good at herding cats. So.
I will, if anyone would like a genuine Arecibo Observatory cat, they can get in touch with me. They can email cats@observatorycats.org. They can follow Observatory Cats on Twitter, Instagram, and Facebook.
Yeah, if you want a space cat, a cat that has participated in science, this is your chance.
Lived next to several megawatt klystrons or half megawatt klystrons for all of its natural life.
And it's only improved.
Get a cat delivered anywhere in the United States.
Awesome.
And possibly Canada. I don't know.
All right. Well, thanks everyone. And we will see you all next week. And then the uncomfortable disconnection. I'm just going to keep talking and press stop stream. And then it's like streaming roulette. When did I stop?